actually going to start doing some hypothesis testing. All of our testing today is going to be around a population proportion. So we kind of talked about setting up the test yesterday, and sometimes the parameter was the mean, sometimes it was proportion. So if we're talking about a sample proportion, that is the p-hat that we're going to be looking at. All the things that we talked about with p-hat are still true and important. So we know p-hat from our formula sheet is x over n. It is normal, assuming the criteria is met. The mean is your p, standard deviation, p times 1 minus p over n, assuming your criteria. Criteria number 1, I've never really made you verify. It just has to be a simple random sample. But we always check that n times p times 1 minus p is greater than 10. And they're independent, meaning the sample has to be less than 5% of the total population. So all of this is on your formula sheet with the exception of the criteria. I don't know that I actually printed this slide. This is just kind of a recap of all the things that we already know about p-hat. So, we are going to be testing to see if something is statistically significant. And that's meaning if the observed results are unlikely under the assumption that the null hypothesis is true. So when we're doing hypothesis testing, we always assume the null is true. And if we get a very small probability, that means if the null hypothesis is true, this is extremely unlikely, so the null is probably not true. If we don't get an unusual probability, does that mean the null hypothesis is true? Not necessarily, it just means we haven't proven that it's not. Alright, so there are 2 different approaches for our hypothesis testing. There is what's called the classical approach, and then there is the p-value approach. I typically only do the p-value approach. I'm going to do one example of the classical, and I think I put one on the homework just so you can see it. And if you really like that method, you are free to use it. The p-value is finding probabilities from the table, so it's more like what we have already been doing. So I really like that. It's just more of the same type of thing. So with the classical approach, you are basically looking at how many standard deviations it is from the mean, or the proportion in this case. So number of standard deviations, that's like a z-score, right? So all we're going to do is look at a z-score and compare it to see is that too far away from the proportion or not. In the p-value approach, we actually find our probability, and then we'll look to see if that probability is unusual or not. So, a researcher obtains a simple random sample of 1,000 people and finds that 534 are in favor of banning the cell phone while driving. So our p-hat is 534 over 1,000. Does this suggest that more than 50% of people favor the policy? Or is it possible that the true proportion is less than 0.5 and we just happen to get a sample where it was more? So we need to find if it would be unusual for this to happen. We need a null and an alternative hypothesis. So we worked on this yesterday. Your null hypothesis is your h sub 0. So we're dealing with proportion. The null is always equal, so it would be the proportion equals what? We're actually not going to do that. We are going to check. The actual question is, does it indicate that more than 50%? So we're actually going to do our null as 0.5, and the alternative, we want to know if it's more than 0.5. The 0.534 is our sample that we're going to look at in a second. Okay. So, if if we're going to do this, if we're talking about P, we have to first make sure it's approximately normal. So, we need to check our criteria. What's that? What are my criteria? Mm-hmm. So my N, we had 1,000. The P is 0.5. 1 minus 0.5. And that equals 250, which is more than 10, so we're good. The other is that my N has to be less than 5% of the total population. We're talking about 1,000 people, and we could assume it's like all people using cell phones, so would that be less than 5%? Yeah. Okay. What's my mean going to be? Just the 0.5. The 0.534 is our p hat that we're going to use later. Okay, so our standard deviation is the square root of p times 1 minus p over n. So far, all of this seeming pretty familiar? We've done that a lot. Okay, so let's think about the classical approach is measuring how many standard deviations something is from the mean, or the proportion in this case. Our proportion is this 0.5. We just found that a standard deviation is 0.0158, so one standard deviation would be 0.5158. If you went the other direction, you would get 0.4842. So if you had something in between those values, that's one standard deviation. If I wanted two standard deviations, what would we do? Yeah, we could basically add your standard deviation again, subtract it again from this side. So you guys kind of remember that setup? So we basically know that if something is way down here, that's several standard deviations from the mean, and what happens to the probability? It gets very small. So that's what we're looking at. How many standard deviations are we from the mean? So if I want my number of standard deviations, what do we have to calculate? Z-score. Yeah, Z-score is how many standard deviations you are from the mean. We're going to talk more about how many standard deviations is too much, and it'll be given in most problems. But if it's not, the standard is 2 standard deviations. If you look back, I don't remember under chapter 3, we had our empirical rule. And it told us then that 95% of the data fell within 2 standard deviations, right? So that leaves 5% on either end. So each end is 0.025. So if you're on either of those ends, then it would be a less than 5% chance, so that would be unusual. So if I don't give you a different threshold, 2 standard deviations would be enough. So we need our Z-score. So Z is our value, which is the 0.534, minus the mean, which was 0.5, divided by our standard deviation, 0.0158. And we get 2.15. So what this means is we are 2.15 standard deviations above the mean. Here is the center. We're all the way over here. So, would that be unusual? Yes. Yes. So, because that is unusual, we reject the null hypothesis. So what that means is if the null hypothesis is true, so if it's true that only 50% of people want to ban cell phones, then there would be a very, very small chance of us getting a set that had 534 individuals. So it is such a small chance to get the data that we got that we would assume then the null hypothesis was not in fact true, and that the actual proportion is not 0.5, it is higher. You guys okay with that? So let's talk about the other way to do it, the p-value approach. So p-value is basically starts off the same. We have to check all of our criteria, get our mean and standard deviation, find our z-score, but then we go ahead and get the probability for that z-score from the table. And then usually we'll have, the problem will give us an alpha level, a confidence level, and if it's more than that, we would decide if we reject or not. So that would usually be given within the problem. If it's not, then we'll stick with our, anything less than 5% is unusual, if I don't tell you otherwise. So the p-value, we're talking about that is just your probability. So it would be the probability of this happening if the null is true. In our example, if you go ahead and look up the 2.15 on our table, so remember we turned this into a z already. We got our z to be 2.15. So greater than, on the table we have to do what? 1 minus, and the number on the table? And we get 0.0158. So if the null hypothesis is true, there's only about a 1.58% chance that this could happen. That is very, very small, very, very unlikely. So that is considered unusual. And we would reject the null hypothesis. We have reason to believe that null hypothesis is not true. Because if it was, this would be a very unlikely result. Does that make sense to everybody? The next few slides, I took the pieces out of your book just so that you would have it on a notes handout if you wanted to look back and reference. And your book just kind of outlines the two different approaches. They start off the same. No matter what, you have a null and an alternative hypothesis. And those, remember, there's 3 options we saw yesterday. The null is always equal, but then your alternative could be not equal, less than, or greater than. After that, we have to have a level of significance. The alpha level, that's probability of making a type 1 error. Remember, type 1 is when we reject the null hypothesis, but we should not have. So that is typically given within the problem. Most of them will say test this if the alpha equals 0.03 level or something like that. Then from there, it depends on what approach you're taking. You'll have to get your z-value. Then, if you're doing the classical approach, you have to have the critical value, which is basically the number of standard deviations that would be acceptable. And you reject if you're outside that window. So then you compare and decide if you reject or not. With the p-value, we go ahead and get the probability, and then if our probability is smaller than our alpha level, we reject. So for me, I think the p-value approach makes more sense just because we've already been looking at these probabilities every time, so it's really nothing different. And what you need to remember is if p is less than alpha, that's when you reject. So if I say the alpha is 0.03, you only reject for a number smaller than 0.03. And then at the end, no matter which approach you're taking, you have to always state your conclusion. So we're going to write a sentence at the end saying there was enough evidence to conclude that the null hypothesis should be rejected, or we cannot prove that we should reject the null hypothesis. let's try, we may do one or two of these today, and then we are not going to finish the whole section, so we'll just look at a couple today. So, in 1997, 46% of Americans said they did not trust the media when it comes to reporting the news fully, accurately, and fairly. In a 2007 poll of 1,010 adults nationwide, 525 say they did not trust the media. At the alpha equals 0.05 level of significance, is there evidence to support the claim that the percentage of Americans that do not trust the media to report fully and accurately has increased since 1997? So, first thing we have to do, null and alternative hypothesis. And I think, did I give you guys a blank slide after these? Okay, good, because they could take a little bit more space. We're talking about a percent, so that's a proportion. The null has to be equal to something. Okay, the original one, that's not from our data, that's from like a previous level or what we've believed it to be. So what is the P in this? The 525 out of 110, that's from our poll. That's going to give us our P hat.
So we want the 0.46.
Yes. We're basing it off the original. In 1997, they said it was 46%. We are testing if it has increased since then. So my alternative would be that P is greater than 0.46. Okay, we know our alpha level. I'm just going to make a note of it. They told us alpha was 0.05. So when would we reject? If our probability is less than 0.05. Okay, let's check if we can do this. Our criteria. N times P times 1 minus P. We need that to be greater than or equal to 10. That's 250, so we are good. My sample has to be less than 5% of the whole population. Would that be the case here? Yeah, so our criteria is met. That means we can do it. Now, what are we going to have to do next?
Find the mean and standard deviation.
Right, no matter what, we have to get a z-score. So if we're going to get a z-score, we need the mean and standard deviation. And that's like what we were doing before. The mean is our p-value. Our standard deviation is the square root of p times 1 minus p over n. And I get 0.0157. So now, we need our z. Z is our value. Do we know our value? Yeah, we need that p hat was 525 over 1010. Or if you divide it, it's not perfect, 0.5198. Our value minus the mean divided by the standard deviation. 3.81.
Do we need to, like, look at the table for that one?
Okay, so what's wrong with looking at the table for this one?
It goes off.
Yeah, does our table even go that far? No. Okay. So from here, I'm going to go ahead for this example and show you both ways of doing it, the classical and the p-value. And then after this one, I'm probably only going to do the p-value approach for all of them. So up until this point, it's the same work no matter which method you do. If you are finishing with the classical approach, we need to find z alpha. So my alpha was 0.05. Okay, that means 5% is to the right, so how much is to the left? 95. So you look in the table, find as close to 0.95 as you can get. So in this case, essentially what that means is that if it's less than this, we're good. We will reject if my z takes me greater than that. So if our z is 3.8, would that be in my reject region? Yes. So I would say since the 3.81 is bigger than the 1.645, reject the null hypothesis. The p-value approach says we have to find the probability. So we need to find the probability that our z is greater than 3.81. Okay, greater than we do 1 minus. The best our table can do, the absolute closest it gives us is 3.49, so we're going to use that. So it was 0.9998, and we get 0.0002. In this case.
Is there a point where it just reaches 1?
Never exactly 1.
Oh, it just keeps getting bigger
Yeah,
decimals.
it'll get closer and closer to 1. So since this is less than alpha, reject. Remember alpha was 0.05?
So how do we find 0.999?
I just did the best my table could do, which was 3.49. That's the
Okay.
highest my table went to. And we know the probability would be even smaller because our table just didn't give it to us. Okay, so do you guys see the difference in the two approaches? It's just this step right here, whether you're measuring standard deviations by finding the z of where we would reject, or if you're looking at the probabilities. And so then, to finish it, we always write a sentence. So, there is enough evidence to conclude. So, we're rejecting the null, so we are concluding the alternative. The proportion has increased.
So your set pattern the sentence has to be in there.
Not necessarily, as long as you are saying, you know, we have enough evidence and telling me what you're concluding. Okay. I'm going to do one more. And this time I'm probably only going to do the p-value approach. So when asked, is it more important to protect the right of Americans to own guns or to control gun ownership? 46% of all Americans said protecting the right to own guns is more important. So what would my null hypothesis be right now? A research center surveyed 1,267 randomly selected Americans with at least a bachelor's degree and found that 539 believed protecting the right to own guns was more important. Does this result suggest the proportion of Americans with at least a bachelor's degree feel differently than the general population? So if I'm testing if they feel differently,
It's not 47.
not equal. All right, let's check our criteria. So n times p times 1 minus p is most definitely greater than or equal to 10, and I'm going to assume that this is less than 5% of the total population. So my criteria are good. We are going to need the mean, the standard deviation, and the p-hat to move forward. So the mean,
24.6.
the standard deviation,
.014 0.
and the p-hat. Excellent. Now what? Z-score. So Z is R value minus the mean divided by the standard deviation. We get negative 1.34. Alright, this one is a little bit different because of my alternative hypothesis. If I just look up this value on my table, it will give me this probability. That's the probability of being less than. But what did my null, or my alternative say? Not equal. That means it can't be this, or remember we said yesterday the not equal was a two-tailed. So we actually need both sides. So we have to think about both of these. But the good news is we can just get it once. This is symmetric, so if we have one of them, we can just take it times 2 and it will give us both. So I'm multiplying by 2 for my probability. And that's because it's a two-tailed test. The only time we'll do that is if it's not equal. Otherwise, we'll just do less than or greater than. So then we look from our table. Negative 1.34 gives us 0.0901. So we get a probability of 0.1802. So that means if the null hypothesis is true, there is about an 18% chance we got a sample like we did. Is that unusual? No. Our guideline here, my alpha was 0.1. We reject if this is less than alpha. This is greater than alpha. So we would fail to reject. Because the probability is bigger than alpha. Does that mean the null hypothesis is true? Not necessarily. It just means I didn't prove it was false. So if I asked you to write a conclusion sentence, there is not enough evidence to conclude the null hypothesis is false. Or you could say something along the lines, we can't prove that the proportion is different. Any questions on that one? So, we can do these on the calculator, but what I'm going to wait and do is show that part to you guys on, a long time from now, in 10 days.
Monday.
So, on your homework packet, we've started 10.2. You could do problem 6, it says to do by hand. Problem 7 is a pretty, just writing your hypothesis and a conclusion, and problem 8 is by hand. So I want you to do 6, 7, and 8, and then stop, because you'll probably want to do the rest of them on the calculator once you learn how. So 6, 7, and 8, those are the questions you should work on.